So it seems all of us are a little bit busy at the end of the July. So let's just have like a short, like the info, like the seminar within an hour today. So I'd like to just continue. So what I introduced from last like the week. So for review, uh, so let's just look at what I already told. So so the reference is statistical Bergman geometry. So there are few things to explain. So this omega denotes just any bounded domain in Cn. So that's a bounded domain. So that it admits the Bergman corner. So we have a Bergman corner from omega cross omega that maps to C, the Bergman corner. So what I introduce is so we define the map. So from this bounded domain to the space of the probability measures. So let me just measure this here. So this means the following. So we also denote dV, the Lebesgue measure, on omega. So in particular, this must be the finite measure because we start from the bounded domain, and we denote also P of omega. This means so we have a dB. So f is in general just a C0, just a C0, and integral of this guy equals 1. And here is a little bit like the subtle that when we talk about the probability density function, then we classical sense require to be positive value, but so this is coming from the Ladon recording, like the theorem that we require this to be just a non-negative. So could be 0, it's possible. But just say, for example, up to like the measure 0, so we kind of ignore, so we just allow to get the just a 0, but cannot be negative. Okay. So we define the map that maps from each z, then the z maps to b omega, the Bergman corner of zz, and we know this is always positive. We know this is always positive, so we take this to be denominator. And for numerator, we take this b sub omega c, and this is now the first lot. And we also change, so let me just write this way. With the absolute value of square, and we take the dv. So it takes c here. So this c is now the free variable. So one can check if one take the integral of this guy. This equals 1 for an easy. So that this becomes the probability density function. And if you look at the form of the integrand here, the denominator is always positive, and the numerator we take the absolute value, so this is always non-negative. So it satisfies the condition I mentioned. So and this map behaves really nicely. Then we have the following. So the reason we care was that if we take the pullback of the so-called Fisher information matrix, then this will give us the Bergman metric. So this is a key reason why we consider this. So let me just also remind what was the Fisher information metric. So recall. So this is theorem A. So recall that. So once we have the probability, so we have a likelihood meaning that I usually just denote like a piece of theta of like the x something like that, and in the statistics like the context this is called by the parameter, but depending on the textbook or the references, so it's also written something like this, doesn't matter. So that for each of the theta, so that you can just think of this as a omega. So this like the z is not chosen as a parameter, and then it determines piece of theta of this guy. And this is called by the likelihood in the statistical context. But this just means nothing but the probability density. Probability density. And then we are able to take, but this can be taken for just being positive in the classical like context, but we are also able to take the natural log, and this is called by a log likelihood function. So that in order to make this to be rigorously okay, then we need to use the Radon-Economy theorem in the data rigorous way to really make sense of it, like they exclude like a measure zero or something like that. And then we have the each of the partial derivatives. If this theta consists of theta 1 to theta n tuple, then we are able to take the derivative of this guy, so that we are not now able to take the L2 inner product for each theta, so that we have, so for each ij runs from 1 to n, so we multiply two functions. In the complex like the context, we just take the complex conjugate depending on the just a context to make it to the inner product. And then we have the expectation with respect to theta. So it just means that we have the parameter space omega, and there's just a Lebesgue measure. And then, so we just put like the P of x theta. Of course, we are taking the integration with respect to x in this context, and then we just put this guy in this way. That's the meaning of the taking the expectation in this context. And this is defined as a Fisher information matrix of the ij component at theta. And then this is just a g sub ij. Let me just the superscript by f. That means the Fisher information matrix. So this is the definition of the Fisher information matrix in the like the statistical model. So in summary, the statistical model has the just a map which is injective here. So from the parameter space to the space of probability distribution, and we define the Fisher information metric in this way. And in our like the case, we have this very like a concrete like the map here. So from this concrete map, so that we can equip with the Fisher information metric here. And we also know that we already equip with the Bergman metric. Then via this like the map described by the Bergman-Connor, then if one just write this like the pullback relation explicit, then one will just recover the Bergman metric. So that was our like like the observation. So the reason why we care, if you have any like questions, let me know. Um, okay. Yeah, Barry, do you have any like the comments or questions?
Yeah, no.
Mhm.
Mm.
So the motivation. So there are actually a few motivations. So the reason, let's see, reason. So yeah, before talking about the reason, because this is the informal seminar, also aiming for research as well. So we're talking about it. So few questions extend this framework. So I'd like the information geometric framework for Kobayashi, Carl Theodori, and Kate. So this is somehow implicit when I look at the references. So, but and I so one of the reason so this works is that so regarding the Bergman metric, we know Bergman metric is a Kähler metric. It's just a special Riemannian metric, preserving the complex structure, preserving the like also the symplectic structure. And the Fisher information matrix also is the Riemannian matrix. So that's why one were able to compare. However, in this like the information geometry framework, so there are, and we know from the like the complex structure variable, like the case that Kobayashi and Carter are not in general Hermitian metric, except like the ball, right? We know it. So we usually correct by the Finsler metric, meaning that we are not able to measure the angle, right? For the Kobayashi and the Carter-Theodori. So information geometry framework does not require the angle. So it's still possible to look at the Finsler version of the Fisher information metric. So one should be also able to compare. So this was not done yet, but I just didn't look at this just seriously. And also the KE metric also has a like a nice like the property. And the in the information geometry, like the context, the Lich curvature also plays some role. So that I think there's also possible like the extension regarding those invariant metrics. So on another like the question that I was thinking for Jocelyn, but he's not showing today, but let me just write this for him. So extend this framework, let me see, information geometry framework for CR geometry. So for example, so one can look at the Ziegel-Conner, and I actually know that my paper done with the Borgman Connor works exactly same for the Ziegel Connor. So this was not written, but this can be done. But it's the same like the argument. So this is not interesting yet, but one can look at further. So in the like the CR like the geometry context, there is a important like the curvature, so-called the Q curvature. So that there should be the way to like extend this like interesting like a context, but yeah, so also I didn't just look at this like the context as well. So yeah, those are some possible like the new like the direction of the questions. And one one other like the reason. So now I'd like to talk about some like the motivating part of like that is like the research. So so as you all of us already know well that complex geometry, complex analysis, several complex variables, those are very, very hard like the topics. So it's hard to even study. It's hard to just get a new result. And so it's a very classical and we know the reality. So this is the way to bridge the mathematical statistics with the theory of the complex analysis. So for like the recent like the 2 decades, so one of the important like the contribution of the mathematical society was the so-called the Schramm-Lohner evolution. I just want to mention some like some motivating part. Some motivating part. So from like the early of the 2000 to right now, so two Fields medals regarding Schramm-Lohner evolution. I kind of don't remember exactly like the, the spelling, but I believe that what I'm wrong is correct. So usually called by SLE. So this is just some topic of the random complex analysis. It's just a describe complex analysis. This describes a random curve on the upper plane or just a disk. So this is the just the mixing two fields between the complex analysis for sure and probability. So It's just a complex analysis and probability. So, and now we know our like the era is a machine learning like the era. So artificial intelligence is everywhere. So and probability and statistics are slightly different and actually quite different. So it is very natural to try to combine complex analysis with the statistics. So in any directions, including the pure mathematics, but there should be also potential like the important like the application in like the different like the fields. So as long as the combination of the complex analysis probability should be so important, turns out to be super important. So it is very also natural to combine statistics with the complex analysis. And this is not the like the field that people are not looking very seriously yet. But I believe that there should be some important application. And at least we know how important the Bergman like the metric and the adjustable is just a Poincare metric, and the Fisher information metric is the standard, like but actually the only unique metric preserving some statistical like the structure. And we know there's just the link. This bridge is something very natural. This is one motivation. And I'd like to also tell, so information geometry. So I need to explain this, but I'd like to say this like the territory is the self like the field of the so-called the optimal transport. After studying some like the topics, one can actually able to like to regard very like naively that the term I'm talking about, the information geometry, is actually self-field of the optimal transport. And the optimal transport is a very like the important topic many like the places right now. And this is about just studying the Monge-Ampere equation, essentially speaking. And we know the Monge-Ampere equation is the way to describe the Kähler-Einstein metric and also the Kähler metric. So I can also see there's some like the informal, like the implicit, like the implication behind. And also there are like some important work of the complex geometry and optimal transfers over by Robert like the Borman. So some like the work so of the references, if you want to look at, is to just look at the work of the Robert Barman, for example. Then he has some, not only him, but I just want to mention one people. Then you can see why the optimal transport can be used like significantly in understanding complex geometry, but also no one actually really look at the information geometry in the like this like the context of the cell field. So there should be some further application. And what I did is the link with the Conner-Bergman metric, whereas the optimal transport usually consider the Monge-Ampere equation. And so we know Bergman metric, there's no like the PD solution, like the perspective. So also there are some gap. So this can be something new. And this is my actual real motivation. The reason is about the embedding. So let me now explain this like the perspective. And so this is also research question. So uh, I believe, let me say this. I believe that there must be something more behind that I don't catch up yet. So you too might be able to get it. So the reason why I want to consider like this like a framework is the following. So compare. So this is what I said last time. So compare this map from omega to this guy that maps from Z to. So I assume to already know it, but just want to just be familiar with this like a form together. So compare this guy with the classical Kobayashi map. Let me say for P. This is a map from omega to so-called CP infinity. CP infinity. So this is just a classical map. So this just means that for each of the point. So I assume all of us are familiar with the definition of a projective space. Yeah,
Yeah,
correct.
what do you mean by PC infinity? Is
So
it a complex projective space?
yeah, complex projective space. So yeah,
It's a half dimension
of
infinity again.
infinite dimension, as you pointed out. So Z naught. So let me just use the standard notation. So here, so I need to define this map, but let me just
Mm,
mention Z naught, Z1, Zn, but it goes forever.
I see, I see.
It
Okay,
goes forever, but this has a linear relation.
okay,
Yeah,
okay, okay.
linear relation by lambda. This lambda is
Yeah,
so
yeah, yeah, got it.
so let me just skip to.
Thanks, thanks, thanks.
So this can
Okay.
be defined in the L2 sense, so that still
Mm,
able to just map this to be. So let me just write down this way, where we have a definition of the infinite dimensional complex projective space. So this is complex manifold of the dimension of infinity, and this S of I is the L2 holomorphic functions on here, so that we just map. So for each of the point to the, so this is infinite dimensional. So this out to like the sense space, like make sense of it, so that we can just map in this way. Then we know that there is a concept of the Fubini-Study metric. So the Fubini-Study metric in general was like the I, the bar, log of 1 plus like the, so the num square like the -1, something like that. But now this is not no longer like the this guy.
yes, yes.
No,
So does this convergence needed here?
series. So
Does
that
any convergence needed?
yeah, so that we just consider when this point just converges. That's the definition of the CP infinity. So that this now becomes
Yes,
from 0 to infinity of this guy.
yes.
So now it becomes infinite for this like the
Yeah,
series. That makes sense to you? So still one can talk
yeah.
about Fubini's to the metric. Is to the metric, then let me just also put this here. So this is just a infinite dimensional extension from the just a finite dimensional is a case. So what Kobayashi showed was that then so also his case is I'd like to say at this point very like the rigorously. So Kobayashi's framework is more general than our framework, even though we consider the same any bounded domain in a sense that some of the propositions that we show we needed to impose additional condition to work the information geometry framework really works, but his like framework does not require any condition. So what I said for the relation here, there's no condition. There's no condition here, but other like the further like the investigation, we need to impose some additional condition. Of course, this works many very like the general classes, but not ever like the bounded domain as far as we figure it out. But yeah, anyhow, so his framework is more general, I should say. So, but what he did is the pullback of the Fubini metric. What do you expect? We will get the Bergman metric. Bergman metric. So this is classical like the result. And this is also very like a powerful result in many different like the senses. However, so now let me just explain why I consider it as this consider new embedding rather than just use the so and you can see some benefit here in a sense that so CP infinity is still complex manifold, even this is infinite dimensional, whereas so this guy is not complex manifold. So P of omega is the space of the probability density. This infinite dimensional Riemannian manifold equipped with the visual information metric, but there's no like at least like the very natural complex structure there. Whereas CP infinity, well, there must be a complex structure. So, but why still we wanted to do this? So the reason is the following. So if you look at omega 1, any bounded domain in Cn, omega 2, any bounded in Cn. So if you consider any holomorphic map, so let's just say F is holomorphic. So this is just very general like a framework. Do you agree? So we always want to look at the like the natural like the morphism in this holomorphic category. And in fact, this is the embedding. So let me denote like this so that we can just embed to CP infinity. Agree? We have each of the bounded domains, then I can just apply this framework for each of the bounded domains for sure. So if you look at this guy, then we know now we have a three maps. We have a three maps. So what do we want to do? We want to induce this guy. That makes the commutative diagram. So this is mathematically very like the natural like the question to ask. Then my question, I have no idea. So how to define this map? I'm not even talking about the relation satisfying this commutative diagram. Of course, we can just define the trivial map. I'm just not talking about this any like the trivial map. So some interesting map talking about this like the diagram. That's what I'm talking about. So I have no idea how to do it. But now let's just consider our framework, omega 1, omega 2. Then now let me just assume this to be measurable, just measurable. So holomorphic function definitely continuous, so it's measurable. So I don't need to explain this for you, any of you. So now we have the another embedding, another embedding. So now we embed, one is this guy, the other is this guy. Is it okay with you? We have this guy. Then can you induce some reasonable map here? So left-hand side, you have a measurable function. Of course, Holorn function is clearly measurable, very measurable. Then how can you embed this like guy? So if you just think about the meaning, so what is the meaning of this guy? So we actually choose the probability measure. So it's just a measure. And you have the so probability measure here. Sorry, you have a probability measure defined on omega 1. Can you induce the probability measure on omega 2? Yes, just say we know if you have a measure here, take the just a pull back or just a push forward. So whatever you would like to call. So there's just a very like the natural way in a sense that so if you have the say for any Borel set B in omega 2, then we know F inverse of B is a Borel set in omega 1. So if you have a probability measure on omega 1, that means that so we have probability measure on omega 2 via this set. So and this is very natural to consider, right? So that if we have a measure on omega 1, then we can induce the measure on omega 2 by just taking the inverse image. So that this is the one reason why we want to change the classical like the framework. So because from CP infinity, but I believe there might be the way to go around, but I just have no idea yet. So you two might have some inspiration here. So if you just compare these two like the different situations by changing the embedding, we can use the inverse image of the measure. Whereas the previous former case, we have no such like the structure from CP infinity. So how can we do that? So that's one reason. And because this like the embedding just requires the all components to be L2 holomorphic functions. So there's no way to move from one L2 holomorphic function to the another L2 holomorphic function, at least natural way, but there should be the way. I don't know. So but I have no idea yet. But this is at least very like the natural from the measure theory perspective. This is one reason. And actually, there's a further reason. So, but I assume up to here you understand my point why we want to like to replace this embedding. Furthermore, so if you look at this framework, this is not the end of the story. So if we define this map chi, you actually see some interesting phenomena. So if you think about the Kobayashi, Carl-Theodori, so what's the key property? Decreasing property. You agree? So when we talk about the Kobayashi metric or the Cartesian metric, so that if you have a holomorphic map, so there's just a natural like the decreasing or the monotonicity. So and we know in general the Bergman does not admit the monotonicity, except few like the special cases such as like the ball or sound. So now let me just copy. Furthermore, now you can see something very interesting. So let me just redraw the same diagram. Let me call this way. And because I have a map F, so that I have a induced map here. Is that okay with you? Induced map here. So now let me ask you the structure. How many Fisher information metrics here? So as long as we have the statistical model, for each of the P of omega, we have the Fisher information metric, right? So for each of the bounded domain omega, then we have the P of omega, and then we define the Fisher information metric. So if you look at here, now we have two bounded domains, omega 1 and omega 2, and we have P of omega 1 and P of omega 2. So that now you can see, let me write like this. Fisher information metric defined on omega 1, Fisher information metric defined on omega 2. So let me write like this. And we already know, by the way, if you take the pullback in the horizontal lines, we recover the Bergman metric. We already know it. Agree? We already know it. Then now let's see something interesting. So if you look at this stage, then if you take the pullback of this guy, what do we know? This equals the Bergman metric on the first bounded domain. We already know it. Now let's look at the vertical line. This line, it's because we have also the map. Then what can we do? Then we can also take the pullback of the second Fisher information metric first, so that we just take the lifting from here to here by using this map chi sub f, right? And then now you can do further, you can also use this horizontal like the shifting by using this guy. Do you agree? You can also do that. Or you can also say as you take the actual pullback of this guy if you want. That's what I meant. So what do we want to do? We want to compare. So can you guess what should be the answer? So this guy, because we compose further for any measurable. And this is the one of the most fundamental inequality in statistical context. So this inequality, so if you have a chance to talk about this in this like people in statistics, so this is a differential geometry interpretation. This is named by so-called the Cramer-Rao inequality in statistics. Of course, the form looks slightly different, but this is exactly like the form of the what they are
Yeah,
usually.
I have a question.
Mhm.
So does the what about the for P2? For P2, the same inequality work? I mean,
It's a good question.
uh,
So yeah, let me first like the talk about this like the part. So that this part is the comparison between the like the pullback of the like the above like the horizontal line, and we take this vertical limiting first, and then we take this part, and then we have this like the inequality called by the Cramer-Rao inequality. What Verdi pointed out is now let's take this part.
yes.
Take this part, then we know from our like the theorem A, so the pullback coincide with the Bergman metric defined on omega 2. then you can also take further like the pullback by using this depth.
Yeah.
So that now what you get is, so if you have this guy, so that you have this one and take the pullback to omega 1. So every comparison is made on omega 1, not on omega 2. Then you also have this guy, this guy. So this fails.
Oh,
So this is the
is this because
monotonicity
of
we are talking.
regularity of F?
So there are many
Am
examples.
am I
Yeah.
audible?
Yep.
Yeah. Is this because of regularity of F? Regularity condition of F? I mean, what happen if you
I
add
really do
holomorphicity
not
for F?
know. This
I
is
see. Okay.
my real motivation to really establish, but also, so what you can see is that this is just nothing but the comparison of the two Bergman metric with the pullback. So yeah, let me just make sure. So this is just a pullback of the Bergman metric without considering our like a context. So there are many, many examples. Usually this fails. Usually this fails. So it's not hard to like generate the examples. The monotonicity fails with respect to the Bergman metric. So, but this is not a like a new like the perspective that at least there is some of the monotonicity with respect to the Bergman metric of the first omega 1. So, but still, however, this is not end of the story. If it seems like so, this is our conjecture. We were not able to solve. So conjecture. So if the diagram commutes, then F must be biholomorphism. So what do we know regarding the biholomorphism? Biholomorphism makes the Born metric to be the same because the invariant matrix means that the any biholomorphism it should be if everything should be preserved. That's the meaning. So if I start from the biholomorphism, then this like a diagram commutes and it's just the same. It's everything is just an equality. Now we have the general situation. If you have a measurable function, then at least some of the inequality holds, some of the inequality in general fails. And what I'm saying is that if this like a diagram commutes, and at least the case of the biholomorph, this is the case. So I'm just asking the reverse. So conversely, so if you have a like a commutative diagram, then can we prove this is biholomorphism? If we start from the holomorphic map, for example, this was our like actually the one of the goal that this gives the characterization of the like the biholomorphism in this like the new framework, but we just fail. So we don't know how to do it. So yeah, this was what we wanted to really get.
Yes.
Mhm. And so this like the fair like the Fairmont like should be measured like the in the like the some non-trivial way, but I still do not know how to do it. Yeah, so now let me just show you some of the like the just the result. Now you can kind of appreciate like the work I explained. Now let me try to explain step by step. So if you two have no other like questions, so now let me just share the paper. It's actually more delicate. Um, so over here, so what I explained is first like this part. So we have the bounded domain, and then so we have a Bergman metric, right? So we have a Bergman metric, and then this is the map that I explained. This is the map I explained. And this is the part also I explained. This is the part I explained. So the Borgman metric coincide with this so-called the covariance of the like the first derivative of the log likelihood function. This is Fisher information metric. They are the same under the condition of the two integrable statistical model. But what we prove is this holds for any bounded domain. So this condition is okay for any like the bounded domain, so that we can, so because of that we can like insist that the Born metric coincide with the Fisher invariant metric in general, because this condition is always correct. However, so and this is now also interesting like the result. So the curvature for tensor with respect to Borgman metric. So if you look at just this form of the curvature like the tensor, this is the exact form of the constant holomorphic sectional curvature up to here. So if the holomorphic sectional, so if the Riemann curvature tensor is written this form, this is the characterization of the constant holomorphic sectional curvature, so that in general there's a additional term because the holomorphic sectional curvature is in general not constant, and the additional like the term is described in terms of the covariance. So purely like the statistical like the quantity. This is what we try to describe. However, this is not free. We need to impose the further condition so that as long as the Bergman corner behave nicely, this is correct, but this we cannot really claim this is for the any like the bounded domain. But still, this is interesting in a sense that the addition like the invariant of curvature invariant other than the constant Horner section curvature is written purely statistical like concept. This is interesting, like the one like the observation. And another like the observation that were able to make was that, so there's a concept of the sufficient statistics. Sufficient statistics just means that I show you the inequality. So let me just explain via the Kramer-Rao inequality. So there are some of the just necessary details to filling the gap of the proofs. So what I explain. So I already told you that, so Kramer-Rao inequality means this guy is always less than or equal to this guy for any measurable function. And we will say, and statistic in the mathematical statistic, it just means nothing but a measure function. You can just interchange from one to the other. So statistics is just any measure like a function. We will say it is sufficient statistic if this is equal. So it just means the official information metric is just preserved. It's just a local isometric, if you know the term of the differential geometry. So showed, what we showed is, so the holomorphic function is, sorry, the measure function is sufficient if and only if the map just behave really nicely, And one possible applications, if you start from the proper holomorphic map, then if you have a like the isometric condition, then that must be the biholomorphism. We know if we have a biholomorphism, this is clearly correct, but we'd like to look at the converse like the direction in order to do it. So this was the application of this theorem B. Of course, there's a way to show this without using this like the framework, but yeah, this is what we aim to show. And lastly, so now we have a statistical like a context, so that in the statistical context, the central limit theorem or the law of large number, those kind of theorems are important like the theorem. So what we show is that we have a convergence via the Bergman metric stochastically. So as long as we have a probably like the statistical model, then there is a way to make the converge for the sequence of the random variable to the complex normal distribution, whose like the covariance is given by the inverse of the Bergman metric. So this is a stochastic like the kind of the description of the Bergman metric in the like some like a funny way. And those are the theorems that we were show. But what we wanted to really like to show that I believe there should be the way to go around, but we still fail, is like the showing this part. So if we start from the commutative diagram, then how can we establish this becomes the biholomorphism? If this is biholomorphism, this must be the case. Everything is just equal. And from my like the paper, we already know what this map explicit. So, and we know this guy. So this guy, those two are also explicit. Then what can we do? So that was what we feel, what we was stuck with it. So yeah, that's what today I wanna explain. And as I told you, so I wanna just look at the next, like the extensions, if any of you are also interested. So these are also next, like the possible looks. Yeah, Aaron, go ahead.
So on any domains, there is a natural way to consider the on one hand, we had this like uh, on any bounded domains, we have the Bergman metric. On the other hand, we have an idea how to construct a Fisher information metric and then relate both. Now, in the first question that you have mentioned over there is to extend it to Kobayashi, Carathéodory, and Keller-Einstein. That's one of the first questions that you mentioned. So now, of course, as you mentioned, it comes with like they can be pseudo metrics like Kobayashi and Carathéodory, and on the information geometric side, do we have only Fisher metric or there are other notions of metric as well when you come to information geometry?
So I understand your question. So two answers. So number one, so P of omega is infinite dimensional Riemannian manifold. Infinite dimensional like the manifold. Let me say it like this. It is just there's a theorem that yeah. Before talking about this theorem, so I just want to make sure that the concept of the where were we? So the concept of the sufficient statistics means that this like the inequality becomes equality. That's the concept of the sufficient statistics. Let me just recall, just a repeat. So if we start from the statistic or measurable function, if we achieve this equality, or in other words, this becomes the local isometric in differential geometry like the term, then we call such a f sufficient statistics. Of course, the context of the calling sufficient statistics completely like the different, but they're actually as an object, they're the same. So there's a known theorem that so if the Riemannian metric on P of omega preserves any sufficient statistics, then it must be the Fisher information metric. There's a theorem. So Fisher information metric is unique in a sense that preserving the sufficient statistics. This is a differential geometric, very like the natural, because isometry should preserve our geometric structure. That is only guarantee for the Fisher information metric in general. This is one answer. Second answer. So what I told you is with respect to the Riemannian metric. Riemannian metric is just the inner product of each tangent spaces, so that for the Carathéodory and Kobayashi, they are not Riemannian metric. They are Finsler metrics. It only takes one vector field. And also there are concept of the Finsler metric on information geometry as well. But this was so there's some like the papers considering the Finsler type of the metric on the P of omega. So it's possible to just look at the Finsler metrics for sure. But if we just impose the Riemannian metric, then it must be the Fisher metric. So in that sense, I believe at least the Kobayashi metric can be considered in this framework because one just need to look at the Finsler metric in this like a new framework and try to just kind of compare. So this was not done before. Yeah. Any other comments or?
Yeah, I have a question.
Mhm.
When we define L2 inner product for the theta, right? I mean, for the uh, Fisher information, I mean, before Fisher information metric. I can go back.
Here?
Yeah. So here we have defined inner product for each theta. Uh, can we define any? I mean, is it possible to define a distance function between two points in the omega using this inner product?
Uh,
Like considering the continuous curve joining two points and evaluating into the Gij, and if we integrate over the line over the interval and considering the infimacing the I mean kind of length, right? Length of the curve with respect to that G.
let me try to like visualize, in a way that
Yeah, exactly.
I
Yeah.
understand. So for example, so let's so this is just embedding to the space of the probability distribution. So this is my omega,
Yes.
this is L is 1 to 1, this is L is 1 to 1, and so that geometry is now preserved so that we choose 2 points, say theta 1, theta 2, so that it maps to P of theta 1 to P of theta 2. And we are looking for the way to just measure this like the arc, either the arc length or the geodesic, for example. Then what we know is the way to do. So if we have the distance between, so either theta 1 and theta 2 or distance. So let me call it like this. So P sub omega, P sub omega of theta 1 or theta 2. So we want to just look at D sub P of omega of P of theta 1 and P sub theta 2. So this is what we'd like to compute, for example. Then we know, so we have the infimum, as you pointed out, of the, or like the C1 curve of this gamma. So let me just fix the parameter from 0 to 1 to omega, right? Because we can just identify, let's take a pullback to the just omega. And this will be integral from 0 to 1 of like the gamma prime of t. So let me record this speaking already C1. So the like the magnitude of this vector with dt of this like the choices of this gamma, and this part we know this is equal to square root of gamma prime t with gamma prime t. And now we see there's the play of the inner product for each of the gamma t. So that let me just put this as a sub of gamma t. So that let me just use the notation as a Riemannian metric with respect to gamma of t of gamma prime of t, gamma prime of t with the square root. So that now we choose this to be just a Fisher information metric. So that meaning that for each of the parameter gamma of t, then we have the inner product with respect to the Fisher information metric, and we just measure the magnitude, and then we take the integral with respect to this like the t. So if we know the form of the Fisher information metric, then we are able to compute. And if the spaces are really like reasonably symmetric, then so this can be computed out. Yeah. So
Okay.
yeah, this is my current like the intuition.
So does this coincide with the Euclidean? No, right? It's not possible.
So for example, if the Fisher information metric is just identically just the identity matrix, then this is just the same as the arc length on just a Euclidean space. But if this like the inner product changes along the gamma of t, then we cannot really like the guarantee. For example, from our seminar, we start from the Poincare metric. Poincare metric, we know this gamma of t, or depending on gamma of t, the Poincare metric are changing. In that,
Yes.
yeah, the arc length must be changed.
So it seems a new metric,
Yeah,
new
this is
distance function, right?
yeah, this is
And there
very
will be
like a
many
natural on the
questions against
statistical
this.
model to measure the distance. So it's already like the
Yes.
useful in like its own way. But it's
Uh,
so one
Is
reason.
there any?
Go ahead.
Yeah. Please go ahead. Yeah. Sorry.
Yeah, no, I just want to mention the geodesic of the Born metric can be also like the link. It should be linked to this like the consideration, right? So if you're able to
Yes.
measure the geodesic distance with respect to Fisher metric, then it coincides with the geodesic distance of Born metric. This is
Yeah,
also
exactly. Because since we are working in injective, embedding function, right? So there will be embedding between omega and p omega. So you can push the geodesic inside the p omega. And it seems there will be lots of questions behind this, lots of geometrical questions with
yeah.
respect to this metric. So when this metric become complete and there is lots of geometrical.
Yeah, for example, the concept of Kobayashi hyperbolicity is very important, meaning that Kobayashi Roida metric induces the topological distance. So if we are able
Yeah.
to make this like the framework, so with the like a replace of the Fisher information metric, then yeah, so this also link the important concept of the complex geometry
Yes. Yes.
analysis
Yes. Yes.
statistics. So this is also
Yeah. Yeah.
interesting.
Is there any reference is anybody discussed, studied those metrics? Those,
Absolutely. So, one reference I recommend to learn this like this subject, so is this one. Um, let me just put some of the references. Let me just put just two references. One is so this article I usually recommend for undergraduate to learn this like the subject if they have no like the any like the background in either differential geometry or whatever they care. And another reference I just want to mention. It's been a while for me. I just mm. Let me put here. So I believe so. This could be the one of the best reference in this like the field. So I'm uploading this to the chat screen. So I think this is very helpful, like the reference. So geometric modeling, probability and statistics. So everything is here. So and also very detailed, so that you can just look at the definition of statistical model and the some like the computations explicit and oh, also by the way, so if I have a chance to also explain further, then they are also very important concept of the complex geometry is a so-called a Calabi diastasis function, and that correspond to the KL divergence or relative entropy. They're actually kind of the same. So you can just look at this like the references full detail. So in my opinion, this could be helpful, but this does not like the really like to look at the Finsler metric in my context. So you know what I mean? Because I want to look at the Kobayashi like the metric. So for that, so one just look at some like the papers, the Finsler like the information, like the geometry, something like that. Okay, so let me today stop the record.
Yeah.